So now let's move on to another question over here. This is example 17.21. So figure 17.23 here shows a linear conductor moving on a pair of metal tracks. Okay, so when we say the linear conductor, PQ is the linear conductor over here, and it's moving on a metal track. And the metal track is this rectangle shaped thing. It's not rectangle, it doesn't have four sides, but it's this shaped thing over here. So this metal track here is like a place for you to put your linear conductor. Okay. So now this linear conductor is moving on a pair of metal tracks with a constant velocity of 2.0 meter per second. So you can say that the speed is 2.0 meter per second, and this is a uniform magnetic field that is directed into the page. Okay, so this time the magnetic field is very clear. They are not just saying it's perpendicular, they are saying it's directed into the page, and they draw it directly pointing into the page. And they also let you see that the conductor is moving to the right, and the motion of the conductor is perpendicular to the magnetic field over here. Okay, then they tell that the resistance is 4 ohm and the length is 0.80 meter. So when we say the length is a length from point P to point Q over here. Okay, so this is the situation we are given with. So let's look at question A. Question A says calculate the induced EMF in the conductor. Okay, so this one, right, why do I call it a changing area question? Is because when you move your linear conductor further and further to the right, what will happen is your initial area is a smaller area. Then through your motion of the conductor to the right, you are making the area larger. Okay, so this is technically also a changing area question actually. Just that the way to do it is slightly similar to the previous question that we do. So that's why I picked this example for us to do together. Okay, again, it's a changing area question. So we are going to find the induced EMF. Let me make sure I write down everything. This is 4 ohm. The length here is 0.80 meter. Okay, so we are asked to find induced EMF. Again, induced EMF is just Faraday's law, d big phi over dt. So now you're going to change it to negative d MVA cos theta. Okay, in this situation here, I'll remove the number of turns n here because over here there's no coil, right? It's just an area enclosed by one wire, one wire, one wire, one wire. So the turns will be just one. So I'll just ignore it. I'll just write BA cos theta. Okay, so now I bring out things that are constant. For me, I can see that the magnetic field is not changing. The only thing I'm changing is the position of the linear conductor. So the magnetic field will still remain as 0.75 Tesla directed into the page. So the B is constant. But the area of the coil, area of the loop over here will be increasing as this PQ linear conductor is moving to the right. It will cause the area to increase. So that will be changing with time. We have to keep inside the differentiation bracket. And lastly, the theta over here. The theta over here is angle between the magnetic field and the area vector. The magnetic field is already pointing into the page. So we can take the area vector to be pointing into the page as well. Okay, so this will not change because you're not changing the orientation of the metal tracks. You're not making the metal tracks rotating. You're not making a metal tracks rotating like this. So if you're not changing the direction or the orientation of the tracks, then the magnetic field direction and the area vector direction should be constant. So the angle between them will be 0 and constant. Okay, so it's the B and the theta that is constant. So we'll bring B and theta out. So it becomes negative B cos theta. Then you have your dA over dt. Okay, so again, I'd like to remind all of you that the area is over here. So this area here can be found by taking the length multiplied by the width. The length they use capital L. the length and the width. Okay, and we can see here as the linear conductor is moving to the right, our width will be increasing with time as the conductor is moving to the right. So what's changing here is not the length. The length is always staying as 0.80 meter. What's changing here is the width. So the width is the one that's changing. So when we modify our equation, we change it to negative b cos theta, then this will be d of length times width dt, but the length, they use capital L. I keep on forget the L. So what we are going to bring out is the length, because the length is constant with time. The length is not changing with time. The negative BL cos theta. The only thing changing is the width over here. Okay, so as we discussed just now, the rate of change of the width is equivalent to the speed over here. As the linear conductor moves to the right with constant speed, the width will be increasing with constant rate as well. So if you move 2 meters per second, means that for every second you are going to move 2 meters to the right, then for every second the width will be increased by 2 meters as well. So the rate of change of width is equivalent to the speed over here. And we see that it caused the area to increase. So therefore, the dA dt here should be positive. Therefore, the dW dt over here should be positive as well, because it causes the area to increase. So because it causes the area to increase, later when we substitute in the speed, we substitute in it in positive. We are not going to do it in negative because the area is increasing due to the motion of the conductor. So it's positive V. Okay, so once we have reached this stage, I believe we are able to substitute everything that we have right now. So this is negative 0.75 times the length, which is 0.80 meter, cos theta, the angle between A and B is 0 degree, then positive V. The V is how much? 2.0. Okay, so you're substituting everything that you have, then I believe you should be able to get the answer of -1.25. Negative 1.2. Okay, again, you can see that the motion of the linear conductor is causing the area to increase. So the increase in area will cause the increase in magnetic flux. So increase in magnetic flux means by d phi over dt here is positive. Therefore, the epsilon here will be negative, because positive times negative, you get negative. That's why your induced EMF is negative value. But here, everything is very defined very clearly. So this negative here will be representing the direction. Okay, so what direction is it in? You can use your thumb. Okay, just now I mentioned the area vector will be pointing into the page. Okay, so if this is your board, your area vector is pointing into the page, then you swipe along your fingers, then it shows clockwise. Okay, if you point your thumb into the page, then you swipe your fingers, it's clockwise. Okay, but as we see in the answer here, it's a negative answer, so it's opposite of what we determined. So opposite of clockwise is anti-clockwise. So that means by our induced EMF here, our induced EMF will be in this direction, anti-clockwise. This will be the direction of the induced EMF. This will be the direction of the induced current flowing through the loop over here. There'll be no current flowing through here, and there'll be no current flowing through here because it does not form a closed loop. So there's no current over here. Or you can say there's no steady current inside here. Okay, so that's the induced EMF in the conductor. And if you want to state it clearly, you can say this is epsilon is 1.2 volt, but you can say it is anti-clockwise. Okay, if you want to state it, you can state it like this. That's fine as well. Okay, Next, they're asked to find the induced current in the conductor. Well, if you know that the loop here has epsilon, but there's no internal resistance, this kind of thing over here. So there's only one resistance, so it's just IR. Okay, last time you have learned that epsilon is equals to I small r plus BR. But here there's no such thing as internal resistance, so it's just epsilon equals to IR. There's no battery over here. Okay, it's the motion here that creates the electromotive force. So it's not like there's a battery there to supply the energy. It's the change of the magnetic flux that supplies the energy to move the charges. So there's no such thing as internal resistance over here. So you just use epsilon is equals to IR. So for this situation here, epsilon is should I put in the sign or not? Okay, if I put in the sign, negative 1.2, then the I here, then the 4.0 will be here. Okay, so if you do your calculation, then I believe your current will be 0.3 ampere. But you get a negative, I think. So the negative here also indicates direction as well. So it's still the same way to indicate the direction. You know that your area vector is pointing into the page, so that's your fingers turning clockwise. So here is negative, so it means it's the opposite of clockwise, and it's anti-clockwise. So if you want to be very clear, you can write down the answer is 0.3 ampere, then you say it's anti-clockwise. But technically, the EMF and the current should all be in the same direction. Okay, so that's question B. Let's move on to question C. Determine the direction of the induced current in the conductor. Okay. So in the conductor, you should expect the induced current to be flowing upwards. This is the linear conductor, so it should flow from Q to P. Okay, so you can just state Q to P. Okay, you can say Q to P, then I think that's enough already. Okay, so if you do follow these equations closely and you substitute, you check the sign properly, then the answer here will tell you the direction of the loop. So if you draw the direction of the loop, then you will know what's the direction of the current that flows through the linear conductor. In this case, it's flowing upwards, so it's from Q to P. Okay, next. Calculate the magnetic force acting on the conductor. Okay, so this is the interesting part right now. Now you're going to integrate what you learned in chapter 5 right now with what you learned in chapter 4. Okay, because what happened? Now you have current flowing in this linear conductor right now. There's current flowing from Q to P, and there's magnetic field in the background. So if you have a current and there's a magnetic field in the background, then this current over here will be, this current carrying conductor here will be experiencing a magnetic force. Okay, so let me clear out the diagram a little bit. There's a current flowing upwards, and there's a magnetic field of 0.75 Tesla. So because there's a current flowing in the uniform magnetic field, you can determine the force by using, okay, you can call it FB maybe. FB is just ILB sine theta. Okay, it's I then L cross B, right? So this is the same thing. I, the current flowing through, is just your answer from B, 0.3. The length here, it's how much? Every time I wipe off things that I cannot copy. 0.80 meter. Then the magnetic field is 0.75 Tesla. Then the angle here is the angle between the current and the magnetic field. Because remember, it's L cross B. So this one is between L and B. Okay, L is the direction of the current. Okay, so the direction of current is flowing upwards. The direction of the current is flowing upwards, and the magnetic field is pointing into the page. Okay, magnetic field is pointing into the page. Your current is flowing outwards. So you check the angle between them. The angle between them is 90 degrees. So that means by it's sine 90 degrees, which is equivalent to 1. So if you multiply everything together, I believe you should be able to get the answer of 0.18 Newton. Okay, so it's getting more and more complex, this diagram over here. So it experiences an induced EMF of 1.2 volt and the current is 0.3 ampere. And therefore, this thing here will experience a force. Okay, and the force that you have determined the magnitude to be 0.18 Newton. What you need to determine now is the direction of the magnetic force acting on the conductor. Well, direction is just L cross B, right? L cross B is the direction of the force. So your direction of the force, your current is flowing upwards, so your fingers will be pointing upwards. And your magnetic field is pointing into the page, so your palm will have to slap into the page. Direction of the current flowing upwards, then your palm slap into the page, then it shows that your thumb is pointing to the left. So if your thumb is pointing to the left, then that means your magnetic force is pointing to the left. Okay, therefore you can say for E, you can see the magnetic force acting on conductor is directed to the left. Again, it's current flowing upwards, then your palm is slapping into the page because the magnetic field is pointing into the page. L cross B, L cross B. So the thumb is pointing to the left, therefore the magnetic force is pointing to the left. Okay, so that's E. Let's move on to F. What is the acceleration of the conductor? Acceleration of the conductor. Okay. They already state for you that this linear conductor PQ is moving with constant velocity, right? Okay, if they tell you it's moving with constant velocity, then immediately you know the acceleration should be 0. Okay, I think what they are trying to highlight is like this. Okay, you have a linear conductor, and the linear conductor is supposed to be moving to the right. Okay, it's moving to the right with constant velocity. So my hand is responsible for pushing it to the right, but the magnetic force is responsible for pushing it to the left. Okay, just now we determined the magnetic force is pointing to the left, right? So my hand, my external force is the one that's pushing it to the right. Then at the same time, the magnetic force is pushing it to the left. So my external force and the magnetic force are both in opposite direction, and because they have the same magnitude, then they will cancel each other out. Net force will be equal to 0. Therefore, the object is able to move with constant velocity. Okay, so because if it's only my hand only pushing with a constant force, it will cause the wire here, the linear conductor here, to be accelerating to the right. If I just push it with constant force, it will be accelerating to the right. But what happened is, because I'm swiping along a magnetic field, then it will create a magnetic force pointing to the left. Due to the induced current, there will be a magnetic force pointing to the left to oppose my push to the right. That's a Lenz's law, actually. Okay, the effect of the magnetic induction, which is the magnetic force, that's the effect of the magnetic induction. Because the magnetic force is due to induced current, therefore the magnetic force experienced by the wire is induced by this motion over here. So the effect is a magnetic force, and the cause is me swiping it to the right. Okay, the cause is me swiping to the right. The effect is the magnetic force pushing to the left. So you can see that the magnetic force pushing to the left is the effect, and it opposes the direction of the cause. The cause is me swiping it to the right. So that's Lenz's law actually. Okay, but we will continue to discuss Lenz's law in greater detail in future videos. Okay, but for question F over here, the acceleration is 0 because it's constant velocity. So you can say moving with constant velocity. Therefore, acceleration is equal to 0. And now you know acceleration is equal to 0. G is just very straightforward. Resultant force should be equal to 0. Okay. So because A is equal to 0, so sum of F is equals to MA. So if this one is 0, then your net force will be 0. Okay. So the resultant force is 0. Okay, so the question here, even though it's a long question, but eventually it all comes out because you're able to calculate A and B properly. If you calculate A and B properly, the others are just relating back to chapter 4 and use your understanding of what is moving at constant velocity, understanding if constant velocity acceleration is 0, then net force will be equal to 0. But the main thing is you have to determine the sign here correctly first. If you determine here the sign wrongly, then your direction will be wrong, then your direction of your current will be wrong, and your direction of your force will be wrong, then everything will be wrong. So you have to be very careful when you're substituting in the velocity over here. Whether it will cause the area to increase or whether it will cause the area to decrease, you have to look at it carefully. Okay, so this is how we solve another question. Example 17.21.